Indian Mathematics Association takes pleasure and privilege in welcoming you all for the third session of the day. Now I request Professor R. Shivaraman sir to introduce our eminent speaker. Please sir.
Thank you, madam. It's my great privilege and pleasure to introduce the esteemed speaker of the third session today. Uh, he's Professor M. Ramurthy from Canada. He obtained his PhD from MIT in the year 1980 and then hold postdoctoral fellowships at Institute of Advanced Studies, Princeton, and Tata Institute of Fundamental Research, Mumbai, the two most prestigious institutes. And he was professor at McGill University during the years from 82 to 1996. And he is presently in Queen's Research Chair and Distinguished University Professor at Queen's University, Canada. There are so many things that we can tell about Professor for all his achievements. I will just highlight the key prizes that he has won for his accomplishments. He has won the Coxter James Prize in the year 1988, Jeffrey William Prize in the year 2003, Queen's Research Prize in the year 2003, and he was elected as Fellow of Royal Society of Canada, that means FRS, in the year 1990, and Fields Institute Prize 2003. He was elected as Fellow of INSA, Indian National Science Academy, in the year 2008, and he was elected as Fellow of American Mathematical Society in the year 2012. I think 2012 marks the 125th birth anniversary of Ramanujan. And he is also a fellow of Canadian Mathematical Society in the year 2018, and he received EWR Stakel Fellowship in the year 1991, and so many other things that I can keep on reading actually. And in 2018, he was awarded the Excellence in Graduate Supervision at Queen's University, and he has published more than 250 research papers, written about a dozen books, and supervised more than 20 doctoral students and 36 postdoctoral theses that he had verified. And he's also cross-appointed at in the Department of Philosophy, where he gives regular lectures on mathematical logic and Indian philosophy. So one thing that I admired him was, apart from his greatness in the academic achievements, he was very simple and down to earth. Three Tamil words that he usually shared with us, and he had been to our association a couple of times and very close to us. And see, there are great people like him who take care of propagating mathematics. We are very fortunate that we have today such an esteemed speaker with us. We welcome you, sir, and thanks for accepting our offer.
Okay, well, thank you very much for your kind introduction. I think I should share my screen first.
Madam? Madam?
Yes? I should share the screen with...
Can you hear me?
Yes.
Yes. Thank you, Professor Shivaraman sir, for introducing such a great personality. So, our association has come up with initiative of releasing an e-magazine titled Mathematical Pixels for meeting our objective of spreading mathematics among everyone. So we are positive that this magazine will reach each and every mathematics enthusiast and students across the world. It's a great privilege for us to request Professor M. Ramurthy from Queen's University, Canada, to inaugurate the release of this e-magazine. Please, sir.
Sir, you can just show the copy.
Okay, well, thank you very much. So I'm sharing the screen. Can you see it?
Yes, sir.
Yes, sir.
I hope you can all see that.
Yes, sir, it's visible. Yes.
Okay, it is my pleasure to have a new magazine called Mathematical Pixels that has been edited by Professors get interested in mathematics because I leafed through the contributions and found all the articles very engaging and interesting, and I'm sure the high school students that Professor Sivaraman has always been teaching will find the magazine helpful.
Okay, sir. Thank you, sir. Thank you
Thank
for listening.
thank you very much, sir.
So should
You
I
can
will
ask.
stop
Yes,
the
sir.
screen now. I will stop the
Yes.
screen now.
Yes.
Can you see my screen?
Not yet, sir.
You can't see my screen. Okay, I'll hold on for a second. Um, I'm not able to find my file after I open that other thing. Can you see my screen?
Not yet, sir. Did you share the screen, sir?
I did. Um, Let me stop sharing then. Okay, so let me. Yeah, I had this open at the beginning, and then I think the other one seemed to have. Okay, let's try this again. Okay, I find it now here. Can you see that?
Yes, sir. Yes, sir.
You can see that?
Yes, sir. It's very clear, sir. We are able to see that.
Okay, so let me know if you can't hear me. Should I start the lecture?
Yes, sir. Please, sir.
Hello?
Yes, sir. You can start, sir.
Should I start the lecture?
Yes, sir. Yes, sir.
Okay,
You can start, sir.
I will just start the lecture then. Hopefully you're able to see the screen. So the title of the talk is Ramanujan Number Theory and the Pandemic. So let me first get the blessings of Ganesha. This is me getting blessings in the Kalahasti temple. So the title of the talk is Ramanujan Number Theory and the Pandemic, and the question that arises is how are the three topics of the title connected? Surprisingly, they are. And the connection between Ramanujan and number theory is obvious. But what Ramanujan has to say about the pandemic is not so clear, and the purpose of this talk is to explain. It turns out that Ramanujan had studied an important functional of the pandemic. So I just want to make sure, can everybody hear me? Is there some way people can tell me if they can hear me? Can people see me and hear me?
Yes, sir, we can see, sir. Sir? Sir, we able to see, sir? Sir, you can proceed, sir. Sir, you can proceed, sir. It's
Perhaps
very clear,
if you
sir.
can tell me either in the chat or something that you can see and hear me, then I can continue. Able to see me. So let me continue then. So the function, the inverse function of the map z goes to z times e to the z is what's called the W function. And this function plays an important role in the study of the pandemic. And it turns out that Ramanujan had studied this function well before it appeared in any works on epidemiology. So let me give you a little crash course on mathematics and epidemiology. The idea of using mathematics to study the spread of disease goes back to Daniel Bernoulli. Here's a picture of Daniel Bernoulli, who in 1760 proposed a mathematical model to study smallpox. But the idea didn't quite catch on, pardon the pun, until 1902. So a good 140 years, 240 years, I guess. 240 years had to elapse before people realized that mathematics can be used to study epidemics in a serious sort of way. So the first person that seems to have started this process is Ronald Ross in the study of malaria. So here's a picture of Ronald Ross. Surprisingly, Ronald Ross was born in Almora, which is in northern India. Many of you may know that. Almora is in the foothills of the Himalayas. So Ronald Ross proposed a mathematical model to study the spread of malaria, and he discovered that mosquitoes were the cause of transmission. So until that time, nobody knew what the cause of malaria was. And his mathematical model actually enabled us to control the spread of malaria. And for that work, he won the 1902 Nobel Prize in Medicine. Later, Hammer and Ross proposed what is now called the SI model for the mathematical study of diseases. The SI model, S stands for susceptible and I stands for infected. It's the most basic model where, of course, there's a serious disease and people are dying off, and they modeled that process using the simple differential equations. This is also essentially the same idea behind the prayer and the predator models of mathematical epidemiology. And they noted that a system of differential equations that governs the growth of these quantities. If you go to Calcutta, you will see in the laboratory where Ronald Ross did his famous work has a plaque on it, and the plaque reads, "In this laboratory, Ronald Ross, surgeon, did his famous work on discovering that malaria is caused by the bite of a mosquito." Now, what I want to discuss here is what's called the SIR model. 1927, Kermack and McKendrick proposed a slightly more complicated model, now called the SIR model. Here, the letter S stands for susceptible and I is the infected number. R stands for the number of recoveries. So when we have a disease on our hands, we want to have also people who recover from that disease. And so we try to model these three functions of time. They're functions of time, and they're related by a system of differential equations. So the first equation says that the rate of change at which the number of susceptible people grows is given by the number of susceptible people at time t times the number of infected people at time t times this quantity beta. So the rate of growth is equal to that. And the rate of growth of the infected people is, of course, the number of people who have succumbed to the disease minus the number of people who have recovered. And the rate of recovery is proportional to a certain gamma. So here, beta is the infection rate and gamma is the recovery rate. So this is perhaps the simplest kind of model that you would use to study the spread of epidemics. And even now, this is essentially the model that's being used. There might be some bells and whistles that are attached to modern epidemiology, but this is basically the underlying idea. So here are pictures of Kermack and McKendrick, who started this important study. So let's try to solve the SIR equation. So let's go back and look at equations again. And I'm hoping that most of you are familiar with basic ideas of calculus. And I'm going to use a little bit of calculus in order to discuss these differential equations. So if you look at this first equation, it's minus beta S of t times I of t. And the last equation is dr by dt is gamma I of t. And so if you notice that if you take the first equation and the last equation and divide one by the other, the i's cancel. So the equation then becomes a very simple equation. It's ds by dr, and then you can solve that. And that simple solution is S of t equals S of 0 times e to the minus beta over gamma times r of t. So what does this say in ordinary terms? It means that the number of people who are susceptible has a certain exponential decay in terms of the number of people who are recovering. So at any given time, the number of susceptible people, infected people, and recovered people is constant. It's the total population. So we'll call that capital N. And if you insert this back into the third equation, that basically I'm taking this S of t plus I of t plus R of t equals N, inserting it back into this third equation, you end up getting that dr by dt is equal to gamma times, so I of t, you see from this equation here, I of t is equal to n minus R of t minus S of t. But then we solve for S of t here, so if you put that back in, you see that dr by dt is equal to gamma times n minus R of t minus S of 0 e to the minus beta over gamma R of t. So this is the basic differential equation governing the behavior of the epidemic. And so let's just go back to that last equation. So you see what we have here on our hands. If you know some basic calculus, you'll see that the what you try to integrate this thing. So you get dr by n minus r minus S of 0 e to the minus r. And it turns out with some basic knowledge that this cannot be integrated. So there's no way you can actually integrate into elementary functions that you already know. It is what is called a new transcendental function. And so this was clear to Kermack and McKendrick, and therefore they sought to get approximate solutions. So let's go back and look at that basic differential equation that's governing the behavior of the epidemic. And the integral that appears in the solution is not an elementary integral. So Kermack and McKendrick were forced to approximate the exponential function by a quadratic polynomial. Most of you may know that the exponential function is given by an infinite series. And if you just use the first three terms in the series, you get an approximation. So the ratio beta over gamma is often denoted R0. It's called the basic reproduction ratio of the disease. Now, usually a disease is under control if the reproduction ratio is less than 1. And it becomes an epidemic if the reproduction ratio is bigger than 1. And in the case of the COVID-19, back in March, April, the reproduction ratio was more than 10. So if we go back and check the differential equation, you see that you have an transcendental function that you have to integrate, and you see immediately that the transcendental function can be approximated by a quadratic polynomial, and so you simplify the differential equation into some sort of a quadratic function. So here, let's not worry too much about this capital N, S of 0, R0, and whatnot. You focus your attention on the fact there's an R here, and there's an R squared here. So essentially, on the right-hand side, I have a quadratic polynomial, a polynomial of second degree. So some first-year calculus now. I'm just going to flash the result. The integral is now more manageable. And we have a differential equation of the form gamma times a plus br plus cr squared, where a, b, and c are given by these terms. Keep in mind, S of 0 is the number of susceptible people at time 0. And so you can integrate this thing, and you end up getting inverse hyperbolic tangent function as the solution. And that's the 1927 paper of Kermack and McKendrick. The novelty of the paper was that it modeled the spread of a disease via 3 differential equations and gave an approximate solution, which was then corroborated by actual events, and the error was not too large. So in this way, they managed to solve the equation, and they also managed to make many predictions which turned out to be pretty well accurate. One of the predictions was they could determine beforehand when the peak of the epidemic was going to occur, the time when that's going to occur, how many deaths will occur before the peak is reached, and how many deaths will occur after the peak is reached. So these are the kind of important findings in the Kermack McKendrick paper. So they were able to predict any pandemic has a peak, and one can foretell when it will occur given the initial parameters and the reproduction ratio. So the final solution, I'm just going to put this up. Don't worry too much if you can't understand everything in there. But the fact of the matter is that R of t is given explicitly in terms of this hyperbolic tangent function. So keep in mind what R of t was. R of t is the number of people who have recovered at time t. We want everybody to recover. I mean, that's the goal of being able to control a pandemic. So if you have a mathematical formula which is going to tell us, given the initial conditions, the initial parameters, how the recovery rate is going to go, this is going to be a very useful tool. And once I have R of t, I can go back to that third differential equation and solve for I of t. I of t is, remember, it's the number of infected people at time t. So the number of infected people at time t is then given by this hyperbolic secant squared function. So the function appearing above in the above theorem is often called the epidemic curve. And if you plot it in Cartesian coordinates, it's a symmetrical bell-shaped curve that reflects what is often seen in epidemics, namely that new cases continue to rise until they hit a certain peak point and then slowly reduce in number. Let us note that this model does not take into account variable rates of infection or removal. One can, for instance, drastically reduce the rate of infection by following the suggested guidelines of personal hygiene, mask wearing, and social distancing with or without a vaccine. And these are the instructions that the governments around the world are telling people to do because we don't have a vaccine yet, or it's soon now it's going to start, but not widely available. And the only way to control this thing is through social behavior. Now, after the 1927 paper of Kermack and McKendrick was written, the question of the error terms began to emerge. And many people thought that their results were off the mark because there was an error. So what is the error incurred in the quadratic approximation? Well, Kumar, Murty, and myself, my brother and I, we started looking at this paper in the 1927 paper in the summer and noted that the error that the paper makes is actually very small. We showed that if you go back and look at that R of t equation, the correction term that's needed is a small constant called phi prime, And the error term is what's called O of 1 over t, which just basically means that it goes to 0 with time. So in other words, R of t can be given explicitly in terms of a hyperbolic tangent function. And this recovery function can be now studied, and we can try to control the pandemic through this understanding. So that's the correction that's needed in the Kermack-McKendrick solution. Now, in 1956, Kendall, D.G. Kendall, this is here, 2007, he wrote a paper which tried to study the Kermack-McKendrick paper, and he shows that you can actually try to give an exact solution by defining a transcendental integral. And then he has another part of his paper, which is essentially calculus of variations, to show that the Kermack-McKendrick solution is not really accurate. So he writes down that the parametric solution of the SIR model is given as a function of time. If you stop trying to give the recovery as a function of time, the susceptible people as a function of time, the infected people as a function of time, but turn it around and ask for the time as a function of these other things, then you can give an explicit formula in terms of an integral. And then if you look at this integral, for those of you who know some basic integral calculus, you see that this integral actually makes sense provided the denominator is not 0. I mean, all of you know that you have a fraction, the denominator shouldn't be 0. So the question arises is, when does the denominator become 0? And so those two zeros, when it does become 0, Kendall showed that there are exactly two terms, zeta minus zeta 1 and zeta 2, for which the denominator becomes 0. And what is the significance of zeta 1 and zeta 2? Well, it turns out zeta 1 is the number of people infected before the peak occurs, and zeta 2 is the number of infected people after the peak has occurred. So these are obviously very important numbers, especially if you want to control something like a pandemic on a global scale. So this leads us to the study of what's called an exponential equation. So you see this bottom line here? It's I of 0 minus zeta plus 1 over R0. Remember, R0 was the reproductive ratio. 1 minus e to the minus R0 zeta. So it's what's called an exponential equation. And this is where this Lambert function comes in. So it opens the study of exponential. We want to solve for R in that equation. And so this leads us to the study of this function called times e to the x. So most of you are probably familiar with the exponential function e to the x. And now if you look at the graph of y equals x times e to the x, it looks something like this picture that I have. But the Lambert function is the inverse function of this function. So that's now, so since some of you may not know what an inverse function is, let me try to explain that. So what is an inverse function? Well, given a function f of x, we say g of x is an inverse function is if f of g of x is x, and if g of f of x is equal to x. That's the intuitive definition. The problem, of course, with the definition is the domain and range have to match up. So here is a kind of a pictorial representation. So I have one set of numbers called a, b, c, another set of numbers called 1, 2, 3, and the function f takes a to 3, b to 1, and c to 2. So what does the inverse function do? It's the inverse function goes in the other direction, and it takes 1 to b, 2 to c, and 3 to a. As you can see, it just flips it around and reverses the arrows. That's the idea. Instead of having finite sets of things, we may have areas in the plane, like a certain blob x in the plane, another blob y in the plane, and so we have a mapping from x into y. And when we talk about the inverse function, we're looking for a mapping y into x, such that these equations, f of g of x equals x and g of x equals x, are satisfied. So intuitively speaking, if I had a curve y equals f of x, so you can see the red curve here, the red curve is y equals f of x, the reflection of that curve on the line y equals x. You see, if you plot the line y equals x, you're going to have a line at 45-degree angle going through the origin. So this is what's called the inverse function. So the Lambert W function was first studied by Lambert in the 18th century, has a long history. He introduced it in 1758 to solve what were called trinomial equations. The trinomial equation is an equation of the form x to the a plus x to the b equals c, something like that. Now we're all familiar with the logarithm function. The logarithm function is the inverse function of the map x goes to e to the x. But the Lambert function is the inverse function to x goes to x times e to the x. Now they may look the same, but they're actually different functions here. And this is an important point. So when I flip that picture that I showed you on the earlier slide, you see that the Lambert function looks something like this. And you can also see that it's uniquely defined on the positive real axis, but when it comes to the negative real axis, it's not uniquely defined, because between 0 and minus 1 over e, as you can see, there are two different values, so that, or what are called two different branches, two different real branches in this case, of the Lambert function. So this leads us to philosophize a little bit about what is mathematics, and in some sense, what is the power of mathematics. The power of mathematics consists in understanding the important role of concepts. After all, numbers are concepts, and for example, the number system has been built out of the decimal system, and the decimal system has a lot to do with the discovery of zero. And when you think about it, zero is an abstract concept. And so this is, let me discuss a little bit about the philosophy of mathematics. And we talk a little bit about the discovery of zero. So here is the earliest known evidence for the use of the modern decimal system dates back to the inscriptions in Indian temples, going back to about 100 CE. CE stands for Common Era. And the best known is the famous Vishnu temple in Gwalior, Madhya Pradesh, where you can see the number 270 right there on the wall. They were trying to, so by that time it means that the decimal system had already come into wide circulation. So now the logarithm and the W function. So we now know the usefulness of the logarithm function. It was a big deal when it was introduced back in the 18th century, the usefulness of the logarithm function. So it's the inverse function of the exponential function, and it's possible to write down a power series for log of 1 minus x. And most of you probably know that. And the question now is, what about, what's called the analytic continuation? So the log of 1 minus x, the expansion, the power series expansion that most of you are familiar with, is valid only for a modulus of x less than 1. And the question arises, is it possible to define the logarithm function in a larger range, a larger domain, so that it makes sense? And this is what's called the problem of analytic continuation in complex analysis. Now, it turns out that these were the questions that Ramanujan was thinking about concerning the W function. That's amazing, because you see the W function appears, I will explain to you, it appears in the analysis of the SIR model. And so W function was already studied well before it made its appearance in the sort of model. So Ramanujan essentially was rediscovering what's called the Lagrange inversion formula. So going back, if I gave you a function f of x and it has a power series expansion, the question then is, what is the power series expansion of f inverse of x? So I explained to you that given a function f, there's something called an inverse function. And now if I had a power series expansion, is it possible to give a power series expansion for f inverse of x? Now Lagrange answered this question. It looks like Ramanujan rediscovered it and applied it to determine the power series of the W function. So here's Lagrange's theorem. Suppose f is, now if you don't understand every word of this thing, don't worry about it, but you'll get a certain sense of it after I'm through with it. Suppose f of z is an analytic function in the neighborhood of z equals 0, and f of 0 is 0, and f prime of 0 is not 0, then f inverse is also analytic in the neighborhood of 0, and then the coefficient of z to the n in the power series expansion of f inverse, that's what the left-hand side means, the coefficient of z to the n in the power series expansion of f inverse of z is equal to the coefficient of z to the n minus 1 of the power series expansion of z to the n over n f of z to the n. So that's a kind of a beautiful theorem. There are very nice proofs of this given for this theorem. And the best, simplest proof that I know uses complex analysis, but there are other proofs which don't use complex analysis, but they're a little bit longer, but they are certainly accessible to the high school student. So Ramanujan's theorem is that, here's a picture of Ramanujan, the Lambert function, the inverse function of z e to the z is actually given by this power series. Summation n going from 1 to infinity 1 over n factorial times z to the n. Isn't that rather amazing? Now, if you know some basic theorems about study of convergent series, it's not difficult to show that this series converges absolutely for mod z less than 1 over e. And in fact, if you look at Ramanujan's collected papers, question 738 on page 332 shows that asks, can you prove that x actually equals this infinite series? So Ramanujan always had the knack of writing things in an exceedingly simple looking fashion. So isn't this amazing? If you were completely new to any real analysis or complex analysis, I mean, this particular expression is so innocent looking and rather inviting. I mean, you look at the simplicity, x equals this infinite series, and you would think, this can't be that hard to prove. Of course, Ramanujan had a clever proof, and that's the proof of this is essentially calculating the inverse function to the Lambert function. So we've written W0 because, like the logarithm, the W function has many branches. I already told you that the Lambert function has 2 real branches, but it has many unknown complex branches also. And what's amazing is that the branches of the W function were discovered only recently in some sense. I will explain that in a second. There are 2 problems that emerge from this initial study. The first is the problem of analytic continuation. The second is that the series expansions for the branches. Surprisingly, both of these problems were solved only recently, and that too partially. The analytic continuation was established by Corliss, Gonnett, Hare, Jeffrey, and Knuth in 1996. Now, if you are familiar with these people's names, especially the last one, Knuth. Knuth is the famous inventor of the word processing, mathematical word processing called TeX. And if you know a little bit more, all these people are computer science people. And so the calculation, the interest in the W function arose from trying to calculate many roots of what are called exponential equations. Now, the infinite series expression for the W function was only worked out recently. In April 2020, Bearden published a paper, here it is, in which he derived a power series for the principal branch that converges for Z, satisfying Z is not equal to, is not on the real line from minus infinity to minus 1 over E. And his expression is this infinite series, summation m going from 1 to infinity, a sub m times square root ez plus 1 minus 1 over square root ez plus 1 plus 1 to the power m, where a sub m is given by this finite sum. You will notice that the finite sum has this expression minus n to the power n minus 1 over n factorial, and these this binomial coefficient and this 4 over e to the n. And the interesting thing about this is that it looks very close to Ramanujan's thing, but Ramanujan's expression only works when the modulus of z is less than 1 over e, but this expression works for all z as long as you're not on that real line segment that Bearden has excluded. It's amazing that this was done only this year. He also indicates how one may derive similar representations for other branches, but he actually doesn't do it. And so this might be a good problem for research for any graduate student listening to study series expressions for other branches of the W function. Now let's go back to that Kendall's paper of 1956 and see that to determine the how to determine the peak of the pandemic, you have to study the roots of the exponential equation of the form a plus br plus e to the cr equals 0. And if you take that equation, you can rewrite it as a plus br times e to the minus cr equals minus 1. That's the nice thing about the exponential function. And you do a little bit of more juggling, and you can see that that equation turns out to be b over c times minus ac over b minus cr times e to the minus cr minus ac over b equals e to the minus ac over b. And the advantage of that is that this exponent is the same as this one. So you can now apply the Lambert inverse function, and you immediately see that minus CR minus AC over B is equal to W sub K times of C e to the minus AC over B divided by B. Now W sub K is the kth branch of the Lambert function. So remember I told you there are countably many branches. W0 is one real branch, W minus 1 is another real branch, and then there are a whole bunch of other layers. So all the roots are given by this expression. And now we understand Kendall's solution to the Sur epidemic model in terms of the Lambert function. He noticed that there were two real zeros in that exponential equation. Well, they correspond to WK equals 0 and K equals minus 1 of the Lambert function. So the real roots, only two are real, the others are non-real, and the two real roots appear in Kendall's solution. And so the positive root zeta 2 can be given in terms of the W0 Lambert function, and the negative root can be given in terms of the W minus 1 Lambert function. And then the final thing is the total number of people infected is the sum of these two roots, zeta 1 plus zeta 2, and you see that it's given in terms of the Lambert function. So you see, in the original Kermack-McKendrick's model, the importance and the significance of the Lambert function wasn't there because it was an approximate solution. In the Kendall approach, he came up against this transcendental function. He knew there was something, but he didn't actually identify the Lambert function in his paper, but he certainly alluded to it through his equations. And it was only much later that people started realizing that if you wanted to get an exact formula for the number of people infected before the peak and the number of people infected after the peak and the total number of infected people, you really need to study this Lambert function. And the surprising thing is that well before the epidemiologists were thinking about the Lambert function, Ramanujan had apparently worked on it and came up with some series expressions for that function. So that's the synopsis of events. So far we've discussed the Sur model of the epidemic and the approximate solution given by the 1927 paper of Kermack and Kendrick. In 1956, Kendall gave an exact solution that involves the Lambert function. He relates the zeros of the function to a number of infected people before and after the peak of the pandemic. By the way, I have to point out in Kendall's paper, the mention of the Lambert function is not there. In 1996, Corliss and others gave the analytic continuation of the W function and showed the existence of a countable number of branches similar to the log function. And then we find out in 1903 in Ramanujan's second notebook, the rediscovery of the Lambert function and the development of the power series expansion. And finally, in 2020, this year, Bearden derives the power series expansion of W of Z valid for all Z in the principal branch. I really don't know what the motivation of Bearden was to do this piece of important work, but certainly it is very timely given the fact that the W function is playing an important role in the study of the pandemic. So some recent joint work with Kumar Murty, special values of the Lambert function are arithmetically interesting. I'm just going to flash this slide about it's basically tells you that if you have alpha 1 to alpha n non-zero algebraic numbers and E1 to En, C1 to Cn are rational numbers, then at least one of the following is true. C1 W alpha 1 plus Cn W alpha is either 0 or transcendental, or W alpha 1 to the power C1, W alpha n to the power Cn. Always, if I were to give you this integral from minus infinity to infinity du over e to the u minus xu squared plus pi squared x squared, well, what kind of a number is that? It's a convergent integral, and it turns out to be a special value of the Lambert function. It's a transcendental number. And if you apply what's called Chanuel's conjecture in transcendental number theory, it talks about the transcendence degree of the field generated by the numbers x1 to xn, e to the x1 to e to the xn. And if you use this sledgehammer conjecture and try and see what it has to say about the Lambert function, you find out that essentially that if alpha 1 to alpha n are algebraic numbers, such that W alpha 1 to W alpha n are linearly independent over Q, then they are algebraically independent. That's what it predicts. In particular, it will predict that W alpha 1 to W alpha n are linearly independent over Q bar. Now this, for the expert listening, who probably knows about Baker's theory of linear forms and logarithms, knows that Baker's theorem says that break numbers alpha 1 to alpha n such that log alpha 1 to log alpha n are linearly independent over Q, then log alpha 1 to log alpha n are linearly independent over Q bar. That's a very powerful theorem. Baker got the Fields Medal for this piece of work. And so now an analogous question shows up with the Lambert function. And if you try to go back to Kendall's paper and try to give an exact formula for the Sur model, you will have to discuss what are called Bell polynomials. So what are Bell polynomials? Well, if you gave me an exponential series summation Cnz to the n over n factorial, it's also a power series, and the coefficients are given by what are called Bell polynomials. You can just take this as the definition of the Bell polynomial. And if you take that as the definition of the Bell polynomial, you can now try to write down an exact solution, and here's how you do it, to the exact solution to the Sur model, and this is how you do it. You first of all take the function a plus bz plus e to the cz and apply complex analysis to it and realize that it's a function of order 1 and therefore has what's called the Hadamard product. The Hadamard product is over the zeros of this function. And the zeros of this function are really special values of the Lambert function. That's the point. So the zeros of this a plus bz plus e to the cz are actually special values of the Lambert function. When you put that back into the Sur model, you get an explicit solution. So I'm just going to flash these slides in the interest of time. A plus br plus e to the cr can be given as an expansion. And then you see that when you write down 1 over a plus br plus e to the cr, which is basically the term that appeared in that integral calculation of Kendall, if you remember, that fraction can be written in terms of this exponential series, where these coefficients omega to the minus n are special values of the Lambert function. And so the power series can be written in terms of the Bell polynomials of the special values of the Lambert function. Finally, you get, by integrating term by term, an explicit formula for the solution to the Sir model of differential equations. So, the Sir model of epidemiology leads to a system of differential equations whose solution gives rise to a new transcendental function called the Lambert function. Surprisingly, this function was studied in Ramanujan in 1903, as entries from his notebooks, both lost and found, show. The study of this function from a complex analytic and number theory perspective opens a new cosmos for us to explore. So if we're able to see this far, if we're able to control, events that seem to be beyond our control, like the pandemic, it is because we're standing on the mountain peaks of mathematics. A century ago, the study of epidemiology, mathematical epidemiology, the study of vaccines was so not as advanced as it is today. And so if we're able to advance to this level, it is because we're standing on the peaks of mathematics. Thank you very much for your attention. Yes. So, are there any questions? I'm not sure if this forum allows for questions. Is Sivaraman here? I've stopped sharing the screen. I hope that's okay. Is the moderator going to come back on?
Okay. So do you hear me now?
I do hear you. I hope I couldn't tell whether you could hear me and see the slides.
Yes, I'm hearing you now, sir.
Okay. What about other people, though?
I think they should also be.
Oh, I hope so.
It's a wonderful lecture, sir. I mean, it opened a new avenue of thinking, actually. It was very interesting, actually. It gave a new perspective. Did you find the connection in Ramanujan's notebook of Lambert function, inverse function?
Yes, I did. Yes. In fact, I have the collected papers at the very end in question 332 or something. He discusses the Lambert function. I mean, he doesn't call it the Lambert function. He calls it 5x.
Yes.
He calls it something else. But it's discussed in the collected papers of Ramanujan.
Okay.
Then,
So that's a very...
Yeah. There's also Ramanujan's notebooks, Bruce Parent.
Yes, I have, sir. Yes.
Part 1. And here, Bruce Parent actually discusses Ramanujan's entries on that very question. So
I have seen that, sir. Yes. But it's one of great connection that you had made, sir. But my question is whether we can check this to current pandemic situation, sir. How far will it be good if you compare the solutions?
Yeah, so you could be pretty accurate. You see, that's the point. The point is the Lambert function will allow you to predict how many people will, when the peak will occur, how many people will die before the peak and how many people will die after the peak. It will determine those given the initial inputs. That's why testing, getting the proper data, getting the reproductive ratio, beta over gamma. All these things are very important. So you need the numerics first. You can't bury your head in the sand and say the problem doesn't exist. You have to get the data, the numerical data. That's why widespread testing and getting the numerical statistics, and then if you plug it in, then you can. This is how modeling is done. Of course, there are more bells and whistles that can be added to this, but I just wanted to give a general exposition so that people see that pure mathematics has value as well.
It is really coincidental that we have discovered that paper, April 2020 paper, which gave the general solution for the power series.
Yeah,
Incidentally, we remember 100th remembrance year of Ramanujan. That there is a fitting tribute, actually.
yes, yeah.
In
And if they're
2020.
graduate students, if they're graduate
April
students,
2020, the general solution was derived, and in 1920 April, Ramanujan passed away. So exactly a century.
yes, it's exactly the same. So what I'm saying there is the problem of trying to figure out the series solutions for the other branches.
Yes.
It's a good problem to work on.
Vijay Kumar, do you have any other questions to share from audience? Any other questions from audience?
So right now there is no question, sir. I'll just put it up.
So, madam, if you wish to ask, you can ask. There are some questions from you. She is a teacher from a college here, sir, and she had done her doctorate in modeling, mathematical modeling, especially in blood cells and other things. So she would be probably interested in this.
It's really very interesting, sir. Actually, how the parameters calculation, alpha, beta, you have mentioned the parameters. And there's a third parameter can be void, or we should consider the third parameter also gamma.
Yeah, so I didn't have alpha, I had beta. Beta was the rate of infection.
Okay, yeah.
Gamma was the rate of recovery.
Gamma, okay.
And beta over gamma is called the reproduction ratio.
Yes.
And if that thing is bigger than 1, we have an epidemic on our hands.
Yes.
And if
Depending
it's-
upon the value we decide. Yes.
Yeah, exactly. You can't control it. So you have to bring that number down. The reproductive ratio has to be brought down to be less than 1, then it's under control. And so with the vaccines now, with the vaccine implementation, you can reduce that ratio. And once that thing is down, then you have what's called herd immunity. Numbers will come down. But the reproductive ratio has to become less than 1 before any significant change takes.
So parameter for calculating the parameters, any specific software can you suggest, or
No,
apart from the
for calculating the parameters, you need specific, precise numerics, statistical data. You have to collect, you have to test, you have to see. That's why the hospitals have to report how many cases they had, how many deaths they had, how many recoveries they had. All this data has to be centrally collected.
okay.
And that's what I'm saying. Mathematics, this is, of course, I discussed only pure mathematics, but there's a statistical component to this thing as well. And the statistical component is the collection of accurate data.
Yes.
I wonder how many of Ramanujan's formula will have such secret connections with other branches. I mean, it keeps on surprising us.
Yes, really.
It's remarkable to see such connections. Okay. So I think we can go to vote of
Thank
thanks
you.
if there are no other questions.
Yes. Thank you, Professor. Now I request Dr. D. Yokesh, Trustee, Pi Mathematics Association, to thank our speaker. Please, sir.
Hello.
Yes, you.
Sir. First of all, thanks.
Switch on your camera, Yogesh. Your camera is not visible. Switch on your camera.
So there is some issues in
Okay, no
camera.
problem.
Sir. Sorry, sir. Okay. So I thank Professor Murty, sir, from Tunes University for his excellent lecture on explaining the concepts of Lambert W function. It is so surprising to see how the concept studied by the Ramanujan will help to find the solution of pandemic situation. Really, we enjoy the session, though it is so late night. But you give a wonderful lecture and make us to um, think in a different way that the concept that was studied by Ramanujan have to be linked with the pandemic problem. I hope that it's a eye-opening for the young research students, and it stands for enter the new domain where they can shine. I wish I thank for the all the audience participants, students who listen this lecture. Even it is so late night, and I thanks once again thanks Ramuti sir for his wonderful lecture and spending his most valuable time with us. On behalf of Pi Mathematics Association, we thank you once again, sir. Thank you so much, sir.
You're welcome.